Hey, welcome everybody. In this video, we're going to talk about something that's not only fundamental to geometry, but really all of mathematics, and that's logic. So this will be the first in a series of videos that gives you a primer on using logic. Uh, it's going to be modeled after what a lot of people in the States will see in a geometry class when the geometry class talks about logic. But this is applicable to many other places, all of mathematics. People who take a discrete math class will see a lot of this stuff. And other kinds of logic classes, you might see some of this, for instance, in certain English classes, philosophy, anywhere that you are being strict about logic. And so we're starting at the foundation. So after watching this video and practicing, you should be able to define the term statement in the context of logic. You should be able to negate a statement that's given to you. And given enough information, you should be able to determine truth values of statements and their negations. So let's get into it. First, what are statements and what do we mean by truth value? Okay, so in logic, a statement is a complete sentence that can be assigned a truth value, meaning that it can objectively be either true or false. Okay, so we think of numbers as having a value, a numeric value. Statements have a truth value. Okay, a number could have the value 5 or negative a half or 2.7 or something. Statements can be either true or false. So first we want to understand what we mean by a statement. So here are 4 complete sentences. Okay, every Tuesday, Julio runs sprints. All clowns are scary. Be sure to get enough sleep. And Tristan thinks mangoes taste good. All of these are complete sentences, but not all of them are what we would call a statement. So if you want, you can go ahead and pause the video and just decide for yourself which ones are statements and which ones aren't. But I'm going to go through it now. So every Tuesday Julio runs sprints. This is a statement. This could be true or false, objectively speaking, right? Part B, all clowns are scary. We would not consider this a statement, not in the context of logic. Although you could argue that maybe it's true, maybe it's false. I'm sure some of you feel very strongly that this statement is true, that this sentence is a true statement. However, in logic, it's very important that that to be a statement, it can be true or false objectively speaking. Okay, so the fact that what's scary is not universal to everybody means that this is not what we would call a statement in the context of logic. Okay, be sure to get enough sleep. This one also is not a statement, okay, although you could say it's important to get enough sleep. The sentence here is really in the form of a command. It's not saying it's important, it's not saying it's good, it's just saying to get sleep. It's telling you to get enough sleep. So this sentence in the form of a command is not what we would call a statement. Part D, Tristan thinks mangoes taste good. Well, this is about Tristan's opinion, right? That's not objective. However, this sentence is stating what Tristan thinks about mangoes. So it is an opinion whether mangoes taste good or not. But because this sentence is specifying Tristan thinks mangoes taste good, that could be true or false. Tristan might think mangoes taste good, Tristan might not. So this is different, for instance, than saying mangoes taste good, which would not be a statement in this context. Tristan thinks mangoes taste good is a statement. All right, let me know in the comments if you have any questions about that. But moving on, here's an exercise. Determine the truth value of each statement below. So in this case, all 4 of these are statements, and the goal is to determine whether the statements are true or false. Again, go ahead and pause if you want to try this independently first. So part A, all squares are rectangles. So to understand whether this is true or false, we do have to know something about what's a square, what's a rectangle, right? So let's say a rectangle is a 4-sided polygon whose angles are all congruent, and a square is a four-sided polygon whose angles are all congruent and whose sides are all congruent, right? So all sides are the same length and all angles are the same measure. For the rectangle, we have four sides, all angles are the same measure. In that case, it is true that all squares are rectangles. Okay, these aren't disjoint sets of shapes. It's actually that all of the set of squares is a subset of the set of rectangles. Every square is a rectangle. Okay, all prime numbers are odd. You have to know what it means for a number to be prime. Let's say we just mean whole numbers. Okay, so a prime whole number would be a number whose only factors are 1 and itself. Okay, any number greater than 1. Okay, that's a stipulation we put on that definition. So, are there any prime numbers that are not odd? Okay, well, 2 only has the factors 1 and 2, 1 in itself. So 2 is considered to be prime. 2 is also even, so this statement is false. Okay. By the way, we call that a counterexample. An example that shows that a statement is false is called a counterexample, and you only ever need one counterexample to determine that a statement is false. All right. 2 plus 9 equals 11. This is a complete sentence. The verb in this sentence would be equals. The subject would be 2 plus 9. Okay. So 2 plus 9 equals 11. Is that true or false? That one happens to be true. Okay. And then a times 1 over a equals 1 for every real number a. Well, I know this is true a lot of the time because most numbers divided by themselves are equal to 1. Is there any number that when you divide it by itself, it's not equal to 1? Well, what if a is 0? Okay, then we have 0 times 1 over 0. But anything divided by 0 is undefined. So since 0 is a real number, and 0 makes the equation false, then this statement overall is false. Okay, because there's a counterexample of a equals 0. Great, let's move on. But again, go ahead and let me know if you have any questions in the comments. So now that we have a better idea of what a statement is and what a truth value of a statement is, let's talk about statements with the word not. That is, talk about negations. Okay, so here we're going to start using variables like we do in algebra, but the variable will take the place of a statement. Okay, the variable is going to represent a statement. So here, if P is a statement, the negation of P always has the opposite truth value of P. Okay, I'm usually going to use the squiggle, the twiddles here. So twiddle P, you can also use this angled thing a lot of places. There are a lot of places where you'll see that for negation, but I'm going to use the twiddle. So we say the negation of P, or for short, we just say not P. Okay, so if you see twiddle P, we usually read that not P. So to illustrate this, here's some set. So in the whole universe, say, lives inside of this green box. And P, okay, that's representing our statement in that circle. Okay, say that's everything where P is true. Okay, in the circle, that's every scenario where P is true. Then not P is going to be every scenario where P is false. So for instance, if P is the statement, the bird is a penguin, right? So if you're thinking of this diagram, you could think of every bird that's a penguin being inside of that circle labeled P. Then what's the negation of P? Not P is the bird is not a penguin. And so every bird that's not a penguin would be in this outer region where it's labeled not P. So if the whole figure here just represents all birds, right, then inside of that circle labeled P, you would have your emperor penguin, king penguin, chin strap, macaroni, rockhopper, all of the different types of penguins would be in that circle. And then outside of that circle, you would have every other bird, pigeons, seagulls, flamingos, hawks, eagles, dodo bird, whatever else. Every other bird that's not a penguin would be outside of that circle. And so this is how we diagram it. When we're talking about the language, we are trying to come up with the exact opposite statement. All right, go ahead and drop a few other penguins and other non-penguins in the comments. So here's an exercise. Given that P is true and Q is false, so P is a statement, Q is a statement. Given that P is a true statement, Q is a false statement, determine the truth values of the following. Okay, so if you want to try this independently, go ahead and pause the video now. I'm gonna jump into it. So part A, we know that P is true. That's given to us. So the twiddles switches the given truth value to its opposite. So the twiddles here is gonna switch this true statement to an overall false one. If P is true, not P is false. We're given that Q is false. And again, the twiddles is just going to switch the truth value to its opposite. So if Q is false, then not Q must be true. Good so far? Okay, so we found out that not Q is true. That was part B. Okay, so we can start there in part C. We know that not Q is true, and now we're negating that. So not Q is true, not Q is the opposite, which is false. So this is effectively our double negation, right? We started with something that was false, and we negated it twice. Turns out that if you negate it twice, it's false. Okay, sort of like when you multiply a number by -1 2 times. Okay, you start with the number that, you end with the number that you started with. Okay, so now we know not Q is false, and we're going to negate that to get not Q. So since not Q is false, not Q would be true. So hopefully what we're getting from this is that the twiddle sign, the negation, only ever switches the truth value of a given statement. So if your given statement is true, not that thing is false. If your given statement is false, not that thing is true. And now we can kind of see this compounding effect. If you continue to negate a statement repeatedly, it will just switch the truth value every time. Here's another one. And again, go ahead and pause it if you want to try this one out on your own first. So we have two statements and we want to write the negation. Okay, so now we're not worried about the truth value necessarily, but we want to be able to negate it. So part A, the drummer was in the pocket all night. So we need to come up with a statement that means the exact opposite, that has the exact opposite truth value. So there are a couple of ways to do it here. One option is to try to include the word not in the appropriate place. Okay, and in this case, we don't just put not in the front of the word. That usually doesn't lead to proper English grammar. Okay, the way that we just put the twiddle in front of the variable. Okay, but in this case, we can include the word not after was. Okay, so one possible way to negate this is the drummer was not in the pocket all night. If the first one is true, then this is false. If the first one was false, then this one is true. So it is a proper negation. It's not the only way to do it, though. Sometimes we want to come up with a negation that sounds a little bit more fluid, a little bit more natural. Maybe one way to do that in this case is to say the drummer was out of pocket some of the night. Okay, and so you can check that both of these statements are negations of the original. They mean the same thing as each other. So if the drummer was not in the pocket all night is true, then it's also true that the drummer was out of pocket some of the night. If the drummer was out of pocket some of the night is false, then it's also false that the drummer was not in the pocket all night. So the truth value between those, the negation and the alternative here, those truth values are the same. And both of them have the opposite truth value of the original. And keep in mind, this is all math. Okay, this is all mathematics. It doesn't mean it's not relevant in English or in writing. And just because we're doing some English and stuff that comes up in writing doesn't mean it's not mathematics. Okay, this really is math. Okay, part B, the bear was over 6 feet tall, so we need something that means the opposite of that, that always has the opposite truth value. So if it's true that the bear was over 6 feet tall, then what's a statement that is going to necessarily be false? One way to do that is to use the phrase at most. The bear was at most 6 feet tall. Okay, so notice if the bear was over 6 feet tall, it can't also be true that the bear was at most 6 feet tall. Okay, if the bear is 6'5", then it's not a max of 6. It's over 6. Okay, so these can't both be true at the same time. And in fact, when one is true, the other is false, and vice versa. Alternatively, we could say the bear was less than or equal to 6 feet tall. We're maybe less likely to use that phrasing in a conversation, but it is a technical way to describe it, and I think it's a good one to have in mind when you're in a math class, because this is the phrasing that we often use when we are dealing with numbers and variables. Okay, so I just wanted to point it out. Again, double check that the negation and the alternative negation are both true at the same time and false at the same time, and that they both have the opposite truth value of the original statement. All right, here's another one. And again, if you want to try this one out on your own, go ahead and pause the video now. But here you're going to negate each statement and determine the truth value of the negation. Okay, so putting a couple of these things together. Part A, every circle has a center. Okay, so first, the negation would be not every circle has a center. In this case, you actually can put not right in front. Okay, so every circle has a center, not every circle has a center. You could say there is a circle without a center. That's how we negate something that has the word every. I'm not going to get into the details today, but do let me know if you have questions about that or want to open it up more in the comments. The negation is going to be false. Why is the negation false? Because every circle has a center. The original statement is true. That is, it is true that every circle has a center. And so since that statement is true, its negation is false. Part B, 11 is an even number. Okay, maybe we should just have it in our head from the start. Is this true or false? Okay, hold that in mind. What's the negation? Well, 11 is not an even number. Okay, again, we can inject the word not in the appropriate place to negate this statement. By the way, since 11 is a whole number, it's either even or odd. And so another way to negate it, arguably, here is that you could say 11 is an odd number. But either way, since 11 is an even number is a false statement, its negation must be true. Okay, it's true that 11 is not an even number. Part C, 16 divided by 4 equals 4. Okay, so what's the negation of this one? 16 divided by 4 is not equal to 4. And in this case, we have a symbol that we can use for the negation of equals. Okay, we have this not equal sign, this inequality with the equal sign with the slash. So the negation is 16 divided by 4 is not equal to 4. Okay, the original statement is true, so the negation must be false. Part D, the product of two positive numbers can be negative. Okay, you can, again, think about whether that's true or false. The negation would be the product of two positive numbers cannot be negative. We can inject the word not in the right place in this case. We can turn the word can into cannot. And what about the truth value? Is the negation true or false? Well, the original statement, okay, the product of two positive numbers can be negative, that's false. Two positive numbers can't make a negative, so the negation has to be true. Okay, so let's recap. Statements are complete sentences that are either true or false, right? Objectively true or false. Whether a statement is true or false is what we call the statement's truth value. And finally, negating a statement causes its truth value to change, either from true to false or false to true. Okay, thanks for watching, everybody. Don't forget to like and subscribe. We have more logic videos on the way. Let me know what questions you have in the comments, as well as any other topics you'd like to see covered on our channel. Okay, see you next time.